Hello everyone. Today we're going to have a short discussion about electric field and field lines. This is to answer some nagging questions, such as, what the heck's going on here? What kind of interactions do we have between this baby positive point charge and this bigger negative point charge? What kind of interaction or electric field exists between them, and how do you calculate it? Next, we have these field lines. What the heck are those? What does it mean that they're pointing this way and that they're that far apart? And then finally, we're going to talk about conductors. And does it matter if it's an imperfectly drawn circle or an imperfectly drawn triangle? I don't know, let's figure it out. To start, let's talk about what an electric field is. An electric field is defined as a region around a charged particle or object within which a force would be exerted on other charged particles or objects. That might sound kind of confusing at first, but I think these equations help explain that a little bit. So let's start off with them. These are just some equations you'll need to understand electric fields, and they're going to be important to your homework, so let's get a hold of what these values mean. For the first equation, we have the electric field E here. You can see E, the electric field, which is defined as F, the electrostatic force, over Q prime, which is, in this case, the test charge. So a test charge means that it's a charge that's small enough to not significantly affect the electric field. So just keep that in mind. The second equation here, we have E, again, the electric field, is equal to KQ. So K is this constant over here, 8.99 times 10 to the 9th. Q is the charge, and that was all over r squared, and r is the distance from the charge Q to the test charge. So just keep in mind those equations are important. Now let's look at field lines and some of their characteristics. At first glance, these lines might seem hard to interpret, but if we understand a few simple rules, they can tell us a lot about the electric field. So, to help us better understand what's going on, let's outline some rules with electric field lines. Firstly, field lines never cross. This is pretty obvious to see in the illustrations over here. You can see that the field lines are never crossing anywhere here. Secondly, we can understand that more dense field lines correlate to a stronger electric field. The more lines that there are in a defined space, the stronger the field. So let's walk through some examples here at the left to make sure that this makes sense. So obviously you see in A and B here that A, the lines are further apart and they're closer together here in B, so that's a stronger field. Kind of a similar thing, but with a point charge here. You can see that this is a stronger field that has more lines coming out of it. This is a weaker field with the lines not as close together. Now this one might be a little more complicated to understand, but F is experiencing a weaker field than E, because to F, if we were to draw like a little circle around it and to draw the same size little circle around E, the lines are closer together in E than they are to F. Okay. So next, we can see that field lines start on a positive charge and end either on a negative charge or go to infinity. This means that arrows will point away from a positive point charge. In fact, we can think of arrows as pointing in the direction that a positive charge would move. This makes sense because like charges repel, so a positive charge would fly away from a positive point charge. On that same train of thought, an electron would move against the arrows of the field lines towards the positive charge. This also makes sense because the opposite charges attract. Lastly, we can see in this illustration that negative point charges have electric field lines that point inward. Okay, let's do something a little fun now. Let's talk about conductors. As you can see, I have prepared for you two different conductors, and just to prove to you that these shapes are real, I have the avocado that I traced, as well as the clementine that I traced. It's a real avocado. It's even got 2 stickers on it. So there you go. So we have field lines here, green for avocado and orange for clementine field lines. You can see that these conductors have different shapes, obviously, because they're different produce. But the first thing that we need to understand about conductors is that electric field lines do not exist within a conductor. So you can see from the inside of the avocado and the inside of the clementine, there's no field lines. You'll also see that the field lines come in or go out perpendicular to the surface. That's also important. The next thing you're going to want to think about is distribution of charge. So as you might expect in a spherical clementine, charge is uniformly distributed, but what you might not expect in the avocado shape is that charge will collect and concentrate in the pointy end. So as you can see up here, the field lines are more concentrated and closer together, and that'll happen on any conductor, that the pointy ends will collect more charge than the more rounded normal ends. Alright, next thing we're going to talk about is when there's an electric field that runs through a conductor. So I traced the clementine again, just for easiness, but you can see that there are electric field lines coming in from the left and going out the right of the conductor. You'll notice that the field lines are still perpendicular to the surface when they go in and when they go out, but you will see that there's polarization within. So the negative charges will concentrate on the left side, the positive charges will concentrate on the right side. This is due to there not being an electric field existing within the conductor, so the charges have to be somewhere. So this is just how it looks. Thought I'd draw a beautiful illustration for you. Let's talk about vectors now. Electric fields can be represented by vectors. This is especially useful when you're solving problems that involve multiple charges that create multiple electric fields. Vectors, as you know, can be added together using a bit of trigonometry. For example, you could calculate the electric field that this green star is experiencing due to the 2 point charges here and here. You would do this using the equations that I showed you at the beginning of the video and then adding the vectors. Okay, that's it for my video about electric fields and electric field lines. Let's have a quick review of the important principles that we learned today. We learned that every charge creates an electric field. Using this equation, we can solve for that. Field lines point from positive to negative, and they never cross. The closer together the field lines are, the stronger the field. Conductors do not have field lines inside them, and field lines end perpendicular to the surface of a conductor. Charges distribute evenly on the surface of a spherical conductor and collect in pointy ends of conductors that aren't spherical. Electric fields are represented by vectors, which you can add together for multiple charges. Thank you.